Hello, fellow students. Today we are going to work on a problem related to connected graphs. So stick around and enjoy yourselves. And this is the exercise that we have for today. Let's read it. It says, given G, an undirected graph, respond in a resonant manner. If G has 10 vertices, how many links must it have as a minimum to have exactly two connected components? So what we can do when we have a problem like this is to try to draw a graph similar to this, right? So let's draw, let's try to do the simplest example, right? If we have something like this, right? We start by B1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, right? Let's write here B10. Well, first of all, we should know what is a connected graph, right? A connected component. But let's say that let's write it down here. A connected graph is a graph where there is a path from any node to any other node in the graph, right? So if I take this one and I wanted it to be connected, I need to have at least, right, a link connecting every node like this, right? With an undirected graph, with something like this, I could access all the nodes right in the graph. So I would need 9 links in this case. But they are asking to have exactly, well, I could have any other link here, right? I could have more links. I could have a link here. I could have another one here, here. But it doesn't matter, right? The minimum number of links that I need for this graph to be connected is one less than the number of nodes, right? This is the minimum. But now they are asking for two components, right? Not the full graph, but to have two components, two connected components of the graph, right? So in that case, I need to remove one link, right? If I remove one link here, well, let's imagine that we don't have this neither, right? In this case, I have two connected components, right? So this is the first connected component. Let's call it C1. And this is the second connected component, right? That I can call C2. So for instance, C1 is equals to the node B1, and C2 is equals to the nodes from B2 to B10. So I need a minimum of 8 links. But now, I mean, what happens if instead of having one isolated vertex here, we want to make this bigger, right? What if we want to, if we say, okay, but instead of only one vertex, I want to have a connected component with 2 vertices here, right? Well, if I have something like this, it means that in this case, neither just imagine that we have all the other nodes here, right? We have all the other nodes here. I think I will draw them all so the picture is more clear. I need to draw 6 vertices here. 1, 2, 3, 4, 5, 6, right? Okay, so if we had a disconnected component, right, with 2 nodes, that means that neither B1 or B2 could be connected to the other connected component, right? Because we want to have 2. So as you can see, we have removed one link from the right part, the right component, connected component, and we have added that link to the connected component on the left. So the end result is the same, right? At the end, we have 8 links. And we could make any change here. We could pass B3 and we would be removing one link here and adding that link on the other side. So at the end, we will always have the same number of links as minimum. So here I have one node here, one link here, sorry. And 7 links on the other connected component. So that means that now C1 is composed by B1 and B2, and C2 is composed by B3 to B10, right? And we have still 2 connected components. So the answer is that we need a minimum of 8 links, right? To have 2 connected components in a graph with 10 in a undirected graph with 10 vertices. Okay, so let's pass to the second sub-question. And here we are asked in general, if the number of vertices is n and the graph has key connected components, what can we say about the number of links in the graph, right? This is the module of the set of vertices, and this is the module of the set of links. Well, in this case, there is a formula. There is a formula that says that the number of arcs must be, sorry, the number of edges must be higher, equal or higher than the number of vertices minus the number of connected components. So in the previous example, the number of links should be greater or equal than the number of nodes, which is 10, minus the number of connected components, which is 2. Right, so this implies that the number of arcs has to be higher or equals to 8. And this is the answer, right? The number of links is greater or equals to 8. This is the answer to this sub-question. Okay, let's go to the next one. And the next question is, is G simple and connected if and only if its adjacency matrix satisfies that, well, it has a 1 in any position of the matrix? Remember that the adjacency matrix, it only tells if 2 nodes are adjacent to each other, right? If there is a path of length 1 from one to the other. So think for a second about it. What is a connected graph? We have defined this already, right? And what is a simple graph? Well, a simple graph is a graph where there is a link, there is a path, from any node to any other node in the graph. So for instance here, oh sorry, that is connected, right? That is a connected graph, right? A simple graph is when there is only one edge between any 2 nodes. So we can see it in the example, right, that we have here. For instance, the easiest in these cases is to look for a counterexample. right? So if we take this connected component, we can see how this is connected, right? And this is simple because we only have one edge between any two nodes. And the adjacency matrix, right, of this graph wouldn't be all ones because this node is not adjacent to V10, for instance. So let's put a simple example here, right? If we have this graph, for instance, right, we can say that it is not true. For instance, the graph on the left is simple and connected, and the position 3, 2 is equals to 0, and the position 2, 3 is equals to 0, being M, the adjacency matrix. Right, so we have put a counterexample. Let's continue. And the final question for this problem is, what if M is the accessibility matrix of the directed version of this graph, right? And we have all ones on that matrix. Well, we could say that we could say, right, in this case, that if it is the accessibility matrix and it has 1 in all the positions, right, that means that the graph is connected because every node is connected to every other node in the graph, right? But we couldn't say that it is simple in that case, right? Because the accessibility matrix, it says if one node is accessible from other, but it doesn't say the number of links that we have between two nodes, right? If only says if it is accessible or not. So let's write the answer. G is connected if and only if the accessibility matrix of the directed version of G is all ones, but we couldn't know if it is simple, because the accessibility matrix does not count the number of links between two nodes, right? If you need to review what is the accessibility matrix and what is the adjacency matrix, please check the previous exercises from the previous lectures. There are some videos where I explain this in detail, and we calculate these matrices. So I will stop sharing the screen now. So thank you very much for joining me today. I hope you enjoyed this lecture. If you have any question or any doubt, please don't hesitate to ask. Also, if I made any mistake, please let me know to correct it, to write a note in the comments. So thank you very much for coming, and I will see you soon. Ciao, ciao.